So here I am trying to work out a few problems in fluids. Let's go to the first one. This is the first question. Talks about a bottle has a mass of 35 grams when empty and 98.44 grams when filled with water. When filled with another fluid, the mass is 88.78 grams. What is the specific gravity of this other fluid? So the idea here is you have a certain bottle that is first filled with water and then filled with another fluid. And you're given the masses and you have to find the specific gravity. Now, specific gravity is another word for relative density. And relative density or specific gravity is the ratio of the density of the liquid to the density of water. So the density of any substance divided by the density of water gives you the relative density or specific gravity. And therefore, what we have to do here is just find out the mass of the liquid filling that bottle divided by the mass of water filling the same bottle. Because we know that the volumes are the same, the volumes will cancel out and the ratio of the masses will give us the ratio of the densities. So that is what I'm doing here. Since the volume is the same, the ratio of the masses will give us the mass ratio of the densities, and so we will get the relative density of the liquid. So the mass of the liquid is 88.78 minus 35. And the mass of water is 98.44 minus 35. In both cases, we have to subtract the mass of the bottle to find just the mass of the liquid or water. And we get the relative density as 0.8477. Do remember that relative density has no units because it's a ratio. Let's move on to the second one. Here is the second question. The gauge pressure in each of the 4 tires of an automobile is 240 kilopascals. If each tire has a footprint of 220 centimeters squared, estimate the mass of the car. So this question basically talks about the gauge pressure. And pressure is force divided by area. In this case, the force is the weight of the car, but the weight of the car is distributed on the 4 tires. But all that is not required here because we're given the gauge pressure directly, and we're also given the footprint. Now, footprint is the area that touches the ground. So all we got to do is remember the definition for pressure and finish the question. We know that pressure is force by area, so mg by A. But the factor 4 comes in because there are 4 tires. And that's why we're using 4. And so mass of the car is 4 times PA by G. P is the pressure given in kilopascals, which I have changed into pascals. A kilo is 1,000, and then area is given in centimeter squared. Do be careful when you change centimeter squared into meter squared. It's times 10 to the negative 4. So, and divide by G, and you get 2.2 times 10 to the power 3 kilograms as the mass of the car. And then you have to look at the answer and think about it, and okay, that sounds right, that could be the mass of a car. Number 3, what are the total force and the absolute pressure on the bottom of a swimming pool, 22.0 meter by 8.5 meter, whose uniform depth is 2.0 meter. What will be the pressure against the side of the pool near the bottom? Again, what are the total force and absolute pressure on the bottom of a swimming pool whose dimensions are given? The dimensions are given as 22.0 by 8.5. So the idea is, by using those dimensions, you can calculate the area of the base, and the area multiplied by the depth gives us the volume. And using the volume, we can calculate the weight of the liquid, and the weight of the liquid is going to be the force applied. So that is the idea. Once you get the force, you can divide it by the area to get the pressure, or just use pressure is equal to H rho G. We only need the height or the depth multiplied with the density and with the acceleration due to gravity. So that is the idea there. So if you're asked to calculate the absolute pressure, remember that you have to add the atmospheric pressure with the hydrostatic pressure. So P sub A is the atmospheric pressure plus rho GH as the pressure due to the water, since we are asked to find the absolute pressure. So we got to add the atmospheric pressure. Here's the atmospheric pressure, 1.013 times 10 to the power 5. Plus, you have the density of water as 10 cube, 1000, times G is 9.80, times H is 2.0. So when you do that math, you get 1.21 times 10 to the power 5 pascals as the pressure. And if you find the pressure, then you can find the force just by multiplying it with the area. And the area is 22 times 8.5. So that gives us the force and the absolute pressure. Number 4. In this question, a house at the bottom of a hill is fed by a full tank of water 5.0 meters deep and connected to the house by a pipe that is 110 meters long at an angle of 58 degrees from the horizontal. So the house is at the bottom of a hill and is fed by a full tank of water 5.0 meter deep. And the pipe is 110 meters long, making an angle of 58 degrees with the horizontal. To find the water gauge pressure at the house and how high could the water shoot if it came vertically out of a broken pipe in front of the house. We surely need a diagram in order to work out this question. So let's go ahead, make this diagram. That's the pipe, and you see the horizontal coming up there. H is the height, and the length is given as 110 meter. The angle is 58 degrees. So that is the house. Okay, so that's the water tank. It's 5 meter deep. So looking at that triangle, we will be able to make out what the height is, because height divided by 110, opposite by hypotenuse, is going to give us sine theta, which is sine 58. And then rearrange that to get the height of the house, 110 sine 58. And from there we can calculate the gauge pressure. Gauge pressure is otherwise the hydrostatic pressure, which is rho GH or H rho G, as you may. Put in the values and calculate the gauge pressure. It's as simple as that. So that gives us 9.6 times 10 to the 5 Newton per meter squared, or pascals. And then how high could the water shoot if it came vertically out of a broken pipe in front of the house? It's going to shoot up to the top of the tank. And to find the height to the top of the tank from the diagram is very clear. Then you got to add 5 meters to 110 times sine 58. So it'll shoot up to 98 meters. That's a big height. Got to make sure that no broken pipe ever happens. A spherical balloon has a radius of 7.35 meter and is filled with helium. That's a big balloon. It's filled with helium. How large a cargo can it lift? Assuming that the skin and the structure of the balloon have a mass of 930 kilogram. Neglect the buoyant force on the cargo volume itself. So what is the topic here? Yes, it is Archimedes Principle. Now, since the balloon is floating in air, air exerts an upward thrust, or in other words, the buoyant force on it, and we have to calculate the buoyant force, and if it should float, then according to the law of flotation, the buoyant force up must be equal to the total weight acting down. Now, the weight is made up of the weight of the skin and the structure, the weight of the helium, and the weight of the cargo. So there are three parts. So when you add all these three weights, it should be equal to the total buoyant force. And how do we calculate the buoyant force? The buoyant force is the weight of air displaced, because air is the fluid in which the balloon is floating. So we're going to calculate the total weight of all of it together. The total weight is the weight of the balloon, which is the skin and the structure, plus the weight of helium, plus the weight of the cargo or the load. Now, weight of the balloon is given. So we have to calculate the weight of helium, and of course from that figure out the weight of the load. And then we have to set this equal to the total buoyant force. Now, what is the buoyant force again? It is equal to the weight of air displaced. And how do we find the weight of air? Weight of anything is volume times density times acceleration due to gravity. So the weight of air displaced is the density of air multiplied by the volume of the balloon, which would be the volume of air displaced. So instead of taking the weight, what I did is you just add the masses of all those three multiplied with g just one time. And that makes it easier because then g gets cancelled from both sides. Therefore, now we can make the mass of the load at the subject, and that's what we get. The density of air will be given in the question. And again, mass of the balloon, which is given, but to find the mass of helium, once again you got to multiply the density of helium with the volume of helium, which is again the volume of the balloon. So I've done some math there, taking out the common quantities as you can see. That's the density of air, 1.29 kilogram per meter cube, minus the density of helium, which is 0.179, times the volume of the balloon is 4 by 3rd pi r cube, because it's a sphere. It says that in the question, a spherical balloon. So 4 by 3 pi r cube. So when you do that and do the math, you would get 920 kilograms as the answer. 920 kilograms. So here is problem number 6. A scuba diver and her gear displays a volume of 65 liter and have a total mass of 68 kilogram. What is the buoyant force on the diver in seawater? Will the diver sink or float? So you given the total volume of the diver and her gear, and you also given the total mass. You have to find the buoyant force. And what is the buoyant force? The buoyant force is the weight of fluid displaced. The fluid here is water, of course, seawater. Its density will be given. And to find the weight, you just multiply the volume of seawater displaced, which is the same as the volume of the scuba diver, times the density of seawater times g. Density of seawater is 1025 times the volume is in liters. You have to remember that 1,000 liters is 1 meter cube. So divide 65 by 1,000 or multiply it with 10 to the negative 3, which is what I've done. And you get 653 Newton. Wait a minute. So she has a total weight of 68 times 9.8. That's the weight of the diver, 68 times 9.8. That comes out to be 666 Newton, but the buoyant force is only 653 Newton. That means she will sink, but she will only sink gradually because the buoyant force is almost equal to the weight of the diver. But she will surely sink. All right, let's move to number 7. So now you have a 5.25 kilogram piece of wood whose specific gravity is 0.50 floating on water. What minimum mass of lead hung from the wood by a string will cause it to sink? See, wood usually floats in water and it has a mass of 5.25 kilogram. Its specific gravity is 0.5. You know what that means? Well, that means its relative density is 0.5. Well, what does that mean? That means when this piece of wood floats, 50% of it will be underwater and 50% will be above. How do I know that? Because that's the specific gravity. It's 0.5, which is 50%. And then the question says, if you keep on adding lead to the wood by means of a string, there's going to be a particular mass of lead which when you add, it sinks. What is that minimum mass? Let's do it. It's again finding the buoyant force and setting it equal to the total weight of wood and lead. That is all. So weight of wood plus lead should be equal to the weight of water displaced. What is the weight of water displaced? The weight of water displaced is going to be volume times density times acceleration due to gravity. I think that's the third time I'm saying that. And to find the weight, you just add the two masses, multiply with g. Same thing on this side. To find the weight of water displaced, do remember that the lead that you're adding is also going to displace its own volume. That's why we have to find the volume of water displaced by the wood. So we have to find the volume of wood and then add it to the volume of lead. So we get the total volume and then multiply it with the density of water. How do you find the volume of wood? Take its mass, divide it by the density of wood. How do you find the volume of lead? Same way, find the mass of lead, divide by its density. So now it's math. What I did here is on the left-hand side, I took out the mass of lead as a common factor, and you will see why. And on the right side, I took the mass of wood outside. Now on the left side, the density of water divided by the density of lead is 1 by 11.3. Well, of course, the 11.3 is the specific gravity of lead which is given. So why did I take 1 by 11.3? Because it's backwards. Specific gravity is what? It's the ratio of density of lead divided by the density of water. But since in the formula you have it backwards, that's why we are having to put 1 by 11.3. Okay, so the mass of wood is 5.2. And then again on the right side, it's 1 by 0.5. And when you do the math, you're going to get 5.7 kilograms. 5.7 kilograms. A 6.0 centimeter diameter pipe gradually narrows to 4.0 centimeters. So it's a big pipe becoming a smaller one. That's what it is. And when water flows through this pipe at a certain rate, the rate is not given. The gauge pressure in these two sections is 32.0 kilopascals and 24.0 kilopascals respectively. What's the volume rate of flow? So what do you mean by volume rate of flow? That means the volume flowing in 1 second. How do we find that? Volume flowing in 1 second is the product of the area of cross section with the velocity. So we can either find the velocity of flow through the bigger part and multiply it with the area of that part, or find the velocity through the smaller part and multiply it with the area of the smaller part. Both will work because both will be equal. Could we find the area of cross section? Yes, because we're given the diameters of both, and we can use pi r squared, circle, because the cross section is circular. We can use pi r squared to find the area of both parts. And how do we find the velocity? We do not know the velocity through the first part, neither do we know the velocity through the narrow part, the wide and the narrow, both. So there are two unknown quantities, and to solve two unknown quantities, we at least need two equations. One of the equations we are going to get using the equation of continuity, which is A1V1 is equal to A2V2. The other one we're going to get using Bernoulli's principle. So that's a 6.0 centimeter part, and that's the 4.0, and we have to find the rate of flow, which is A1V1 or A2V2. Okay, so that is one equation, and to find the area of cross section, it's pi r squared. Remember, I'm not changing centimeter into meter because you have the same, you have consistent units on both sides, so that's okay. And when you do that math, pi's will cancel out and you get that 9, because 3 squared and 2 squared is 4. And then from here, we are getting V1 and V2 onto one side because we want to substitute for V1. So V1 is 4 by 9 V2, so you got to square it. And I've just taken 2 common factor from the left side and so brought it to the right side, multiplying it with 2. That's what I've done there. And then in place of V2, we could write 9V1 by 4. Either way, you could either substitute for V1 or V2. And because there is a square, that's why it became 81 by 16 V1 squared. 9 squared is 81, 4 squared is 16. And then out of this, we have to find the value of V1. So there is some process there. So here we go. This is what we had. I am taking out V1 squared common. 1 minus 5.0625. That's what I get when I do 81 by 16. And then 2 times P2 minus P1 by rho. 1 minus 5.0625 is taken. And then we know that rho is the density of water. Okay, 1 minus 5.0625 is negative 4.0625. Do not worry about the negative yet, because you're also going to get P2 minus P1 as negative. Remember, P2 was 24 kilopascals and P1 was 32 kilopascals. So that's also going to be negative, and 2 negatives make a positive. So when you do the math, all right, the density of water is 1,000. That's why you see 10 cube appearing there. When you do the math, you get V1 squared as 3.93. Take the square root and you would get 1.98 meter per second. And once we have that velocity, you can multiply that velocity with the area of cross section of that part. Now I have to change centimeter into meter. That's why you have 0.03, because it's not a ratio anymore. You have to get the actual value. And when you do that, you get it in a meter cube per second, so it's going to be a small number. The reason is 1 meter cube is such a huge volume. That's why we get that. If wind blows at 35 meter per second over a house, what is the net force on the roof if its area is 240 meters squared and it is flat? Wow. We're talking about a very strong wind blowing over the top of a house. So we have 2 points now. One is above the roof, the other is below the roof. And below the roof, of course, inside the house, air is not moving significantly, or the speed of airflow, maybe due to the AC or whatever, it's almost zero. So at one point it's moving at 35 meters per second, which is really fast. Just below the roof, it's not moving. And you know from Bernoulli's principle that where the speed is higher, the pressure is lower. So over the entire roof, the pressure is going to be much lower. And if you find the pressure difference between the top and the bottom of the roof, and multiply it with the area of the roof, which is given, which is huge, you would get the force that acts on the roof. And many a time, this force is enough to tear the roof off the nails and take it away. Hope it doesn't happen to any one of us. But that is the force of nature. Pressure difference, P2 minus P1 times A, where P2 is the pressure below, P1 is the pressure above. Because P2 is going to be greater than P1, right? Where the speed is higher, pressure is lower. And this is Bernoulli's principle. P1 plus 1/2 V1 rho V1 squared is P2 plus 1/2 rho V2 squared. I changed the diagram because I recognized that it said it's a flat roof. So P2 minus P1 is 1/2 rho V1 squared minus V2 squared. Bringing, the terms to the left and the right. And then force is P2 minus P1 times the area. And therefore, it's just 1/2 rho V1 squared minus V2 squared times the area. Rho is, of course, the density of air, which will be given. It's given as 1.29 kilogram per meter cube. And next, remember I said V2 is 0. And V1 is given as 35. So put that and multiply it with the area. The area is 240. And when you do the calculations, you get 1.9 times 10 to the power 5 newtons. My goodness, that's a lot of force. That's 0.19 million newtons. So on to the last question. Estimate the air pressure inside a Category 5 hurricane where the wind speed is 300 km per hour. Now we're calculating the wind speed in a hurricane. Inside, this is a Category 5 hurricane, and we have to find the air pressure inside. And the wind speed is 300 kilometers per hour. First of all, kilometer per hour will not work. You have to change it into meter per second. And then we have to apply Bernoulli's principle. So the wind speed outside, just like in the case of the roof, where we assume the airspeed at the bottom to be 0, we have to assume that the wind speed outside is 0. It's not exactly correct, but compared to 300 km per hour on the inside, the speed on the outside is negligible, so we can take it as 0. Okay? Because it'll be very small, almost close to 0. So the pressure outside is the air pressure. What does that mean? It's the atmospheric pressure. So on the outside, the air is not moving. Therefore, the pressure there is the atmospheric pressure. And now we have our 2 points. The 2 points are, one is the outside, the other is the inside. And then applying Bernoulli's principle, which is coming right there. I've written it as inside and outside instead of writing it as P1 and 2 just to avoid confusion. We are looking for the pressure inside, so that's what we're trying to find. Once again, rho is the density of air. And I am taking that term to the other side, to the 1/2 rho v squared outside. Well, if the velocity is 0, that entire term becomes 0. Velocity outside is 0. Remember that. That's why that whole quantity is 0. That's why you don't have it. Then 1/2 times 1.29 times, you see 300 times 5 by 18. That is the easier way to change kilometer per hour into meter per second. Multiply by 5, divide by 18, and you get 9.7 times 10 to the 4 pascals, which is 0.96 atmospheres. How do you get that? By dividing pascals with 101,325, because 1 atmosphere is 101,325 pascals. So now we have finished 10 questions, and I hope you will take the time to understand these 10 questions and do good on the next exam. Thank you.